Solve problem 4.7 from the book Applied Thermodynamics, McConkey and Eastop. Here is the statement. A 1 kg of air is allowed to expand reversibly in a cylinder behind a piston in such a way that the temperature remains constant, that is 260 centigrade, while the volume is doubled. The piston is then moved in and heat is rejected by the air reversibly at a constant pressure until the volume is the same as it was initially. Calculate the net heat flow and the overall change of entropy. Sketch the process on a TS diagram. So the mass, that is 1 kg, the temperature T1 and T2 is taken place at a constant temperatures, that is 260 centigrade. If you add 273 with it, it will convert into Kelvin, that becomes 533 Kelvin. So the heat is supplied at a constant temperature, still its volume, final volume becomes equal to 2 times of its initial volume. That is given in the statement. Then the piston is then moved in, so heat rejection is taken place. So the second process that is taken place at a constant pressure. So let me draw its TS diagram. So here is the temperatures T1, T2, that is same, that is equal to 533 Kelvin. So the process continuously supplied the heat Q from process 1 to 2 at a constant temperature such that its volume increases double of its initials. So this case the temperature is constant. Now the piston is moved inside and heat rejection takes place. So it is obvious if there is a heat rejection takes place, the entropy will drop and the corresponding temperatures will also drop. So this is 1 to 2 up to 3. Now at 2 the entropy is S2 and entropy at 1, that is S1. So this heat rejections that is takes place at a constant pressure. So this is the constant pressure line. So you can say that the pressures at 2 to 3 that is equal. So you can say that the pressure P2 will be equal to P3. Now come to the solutions. So now consider this process 2 to 3, that is constant pressures. If the pressure is constant, then the volume to temperature relationships, you can find the temperature T3 value, that is our concerns and our requirement. So I can write T3 divided by V3, that is equal to T2 divided by V2. Remember, here the statement is given that at constant pressures, when heat rejection is taking place, the volume V1 and V3 is the same. So V1 that will be equal to V3. So I can say that V3 is equal to V2 divided by 2. Plus V1 is equal to V3. So I can say that V3 is equal to V2 by 2. So the final temperature T3 that we need is equal to T2 multiplied by 1 over V2 multiply this, that is V3, and this V3 is equal to V2 divided by 2. So this V2 will be cancelled out with this V2, and the temperature T2 that is 533 Kelvin. 533 divided by 2 you will get the temperature T3 that is equal to 266.5 Kelvin. Now next is the heat that is supplied during this process 1 to 2. It is equal to Q 1 to 2, that is equal to R T1 ln V2 divided by V1. So what is R? That is constant 0.287. What is T1? That is 288 ln, and this volume ratio, that is 2. So upon simplifications you will get the value that is equal to 106.1 kilojoule per kg is the heat that is supplied from process 1 to 2. Next, the heat that is rejection taking place from process 2 to 3, that is equal to 2 to 3 is Cp, and change in temperatures, that is final stage temperature minus from where it start to T2, minus 268 kilojoule per kg. Now the net heat that is supplied or rejected during this process, that is equal to 106.1 minus 268, and you will get that is minus 161.9 kilojoule per kg. It means that the net heat is rejected, not supplied. Next we need to find the change in entropy, V2 divided by V1. What is CV? 0.718 ln 2. On simplification you will get the change in entropy during this process, you will get that is 0.4976 kilojoule per kg Kelvin, and this is the final answer.